In a two-body problem, now every problem that we do is a two-body problem, but here we're specifically referring to situations where the two masses involved are not too different. So we do not treat one mass as fixed and then the other one doing all the motion. Both planets or both stars or both objects are moving. In this situation, we trace the line between the two objects, and there will be a point at the center, which is the center of gravity, which is calculated the same way you were taught in mechanics. So this center of gravity is the fixed point in the orbit. So you would have both masses circling around in elliptical or circular orbits around the center of gravity. If the separation between the two objects is actually ultimately the semi-major axis of the orbit, and I will get back to this little detail later, but I would say that the distance r1 would be the distance from m1 to the center of gravity. So this is the center of gravity, and I would define r2 to be the distance between the second mass and the center of gravity. Now this is very, very important. r1 and r2 are not equal to the periapsis and apoapsis. In an ellipse, we define r1 and r2 as the closest point and furthest point of the orbit. This happens to be the same symbol, the same notation, but this is totally unrelated. So r1 and r2 refer to mass 1 and mass 2 and how far they are to the center of gravity. Okay, so this has absolutely no connection with r1 and r2, the periapsis and apoapsis in an ellipse. Now, we will derive in class the relationship between r1 and r2 and then the masses, and then we will find out that the heavier is the mass, the smaller is the radius. In other words, the heavier is the mass, the closer it gets to the center of gravity. And ultimately, when the mass m1 is infinitely heavier than the mass m2, then it makes sense that the mass m1 becomes pretty much the center of gravity, fixed, and then only m2 moves. Right? So that would be the typical situation of a planet around a star. So anyway, here we have m1 r1 equal m2 r2, and you can see that when a mass increases, to keep this equality, its distance to the center of gravity decreases. All right. So now these orbits, what do they look like? Well, if one mass, say, is 4 or 5 times bigger than the other, the center of gravity would be very close to it. If the orbits are circular, then both objects would be moving in a circle around their common center of gravity. So this is a terrible circle. But you get the idea. Here's a nice circle. Now, whenever one mass is on any place in its orbit, if you draw a straight line through the center of gravity, you can find the second mass. In other words, they will always be in direct opposition when compared to the center of gravity. They'll complete their own orbits in the same time interval. When the orbits have a larger eccentricity, then things get a bit more complex. So for example, here I would draw, this is the center of gravity. We also call it barycenter. Here's the mass m1. And let's say this is the ellipse describing the orbit of m1. And I better erase this drawing here. I need space. Now let's imagine a less massive companion of mass m2 when the mass m1 is at its periapsis here. The second mass would also be at its periapsis. So let's say this would be the position of the mass m2 at periapsis. This will be the shortest distance to the center of gravity. Now, the orbit here would be a larger ellipse, which essentially is a mirror of the orbit of m1, except much bigger. And if you look at the orbit of m1, its apoapsis is over here. This is the farthest point from the center of gravity, in which case, for M2, the apoapsis would be over here. So the two orbits will always maintain this straight opposition. When M2 is at some point in its orbit, M1 would be in the opposite. So you can see that the two orbits cross each other. However, the two masses will never collide because they are always in opposite direction, in opposite position relative to the center of gravity, always completing their orbits in the same amount of time. This can be complex, and therefore, when we deal with two-body problems with two moving masses, there is a very simple transposition that we do. We take a coordinate system, well, not here, but here. We take our coordinate system to be centered on the heavier of the two masses. So that mass will always be at the origin. So this is a coordinate system that moves with M1. From this perspective, from the perspective of the heavier mass, the second mass will always be at a distance equal to R1 plus R2. And so look at this distance here. The mass M2 would appear to be 1, 2, 3 squares to the left, would be here. And then half of a period later, the mass M1 is at this side, and the mass M2 would be over here. So from the perspective of M1, the mass M2 is 1, 2, 3, 4, 5, 6, 7, 8, 9 squares to the right. So this is M1, this is M2 at this position, and then half a period later, M2 has moved 9 squares to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, something like this. So what we have here is a much bigger ellipse that M2 describes around M1. And the radius of this ellipse, or the semi-major axis of this ellipse in this case, the semi-major axis of this ellipse will be equal to the semi-major axis of the ellipse of M1 around the center of gravity plus the semi-major axis of M2 around the center of gravity.